Okay, good morning. Let's take a seat. Let's get started, okay? Okay, so where are we standing in the course? Okay, so essentially last time, modulo, a couple of slides, we finished talking about, the second part of the course where we are looking at analysis tools, that is, tools that allow us to understand how the system will behave, especially in terms of how the system will behave after we close the loop, okay? Based on the knowledge of how the system behaves in open loop, okay? Again, this is the whole point of classical control methods. What we do in this class is to learn as much as we can about the closed loop just based on the knowledge of the open loop transfer function, okay, or the open loop model. What we start doing today, and we will do, throughout the end of the, to the end of the course, is really looking at how we can use these tools actually to get some guidelines, some principles for designing a control system that makes our closed loop behave in a way that we like. Before we do that, we need to really, talk about how do we say what it is that, how it is that we want our closed loop system to behave, okay? So this is what are called specifications, right? So this is how your boss will tell you what he wants you to do, okay? Design a control system that achieves this and this and this property, okay? So we'll do that today, and then the next 4 lectures will be about, techniques to actually do that, okay? Now, before we do that, we need to finish the last 2-3 slides from the last lecture, okay? So if you remember what we said in the last lecture, we're talking about this, like a Nyquist plots, the Nyquist criterion. What we said at the end of the day was something like this, right? That what we wrote is Z is equal to N plus P, okay? Z is the zeros of the characteristic polynomial in the right half plane, right, with positive real part. And these are the unstable closed loop poles, okay? So Z is the number of unstable closed loop poles, okay? And the number of unstable closed loop poles is given by the sum of P, which is the number of unstable open loop poles, okay? And N, which is the number of encirclements of the -1 point, okay? So, in particular, if I know that my open loop system is stable, meaning, so what is P? If my open loop system is stable, what is P? Anybody? 0, right? So if my open loop system is stable, then P is equal to 0. Then to make sure that my closed loop system is also stable, then what do we need to make sure of? We need to make sure of that N is equal to 0, right? So we want Z to be equal to 0. We know that P is equal to 0. We need N to be equal to 0, okay? So what we know is that, so let me draw the, like a Nyquist plot here. Okay, so let's say that this is the complex plane. We have the -1 point here, okay? Then what I want is that, let's see how long this lasts. So what I want is that my Nyquist plot, can be anything, right? As long as it does not, encircle the -1 point, okay? You see that? You know, as long as I don't go around the -1 point when I draw my Nyquist plot, then I know that my closed loop system will be stable. Okay? Now, something that is very important to keep in mind is this notion of robustness, okay? So now, if my Nyquist plot does not go around the -1 point, yeah.
Why are we looking on -1? Why not 1 or 0?
Remember that, you know, the characteristic equation, the characteristic polynomial, right? So let me write it here. You know, the characteristic polynomial, or characteristic equation is 1 plus L of S is equal to 0, right? Right. So then, when we draw the, when we draw the Nyquist plot, what we are plotting is actually the polar plot of L of S, right? So really, what we are looking at is the number of encirclements of the origin by this function here. Okay. For convenience, instead of plotting this function here and looking at the number of encirclements on the origin, what I will do is I will write the same thing as L of S is equal to -1. And then what I will do is I will count the number of encirclements of the -1 point of this function, but you're looking at the encirclements of -1. Okay, so was the question there in the back?
If I do the same thing for a feedback system with a parameter K.
Why? So if you do this, so if I write this, I may want to write this as 1 plus K, right? L of S. So then when I do this thing, then this becomes -1 over K. Okay, so then the -1 point will become -1 over K, right? If you're thinking of K as a parameter. Now what I'm saying here is that you essentially fix K, right? Once you fix K and you put that inside L, then you're looking at the encirclements of the -1 point. There was another question around here? It was the same question, okay. Okay? Good, so now the point is, okay, the number one thing that you have to remember about models is that the model is not reality, right? So chances are, actually guarantee you that your model will be wrong. Okay? So now an important question that you must think of is, how robust is my design? Okay? How far am I from being unstable? How do you measure this, how far you are from being unstable in this Nyquist plot? So essentially what I want is that I don't want this curve to ever get close to this -1 point, right? Because as soon as you go over it, then you will encircle it, right? So in a sense, the notion of, of robustness, you can think of it as something that tells you, how far away I am from this -1 point, okay? The furthest you are, the more robust your design will be, right? Because now you can have some errors in your transfer function, and still you will not get close to the -1 point, okay? Now, in principle, really what you would like to figure out is what is the radius of this circle, right? So you want to make that circle as large as possible, okay? In practice, what is often done is that you don't measure that circle necessarily. What you measure is other two quantities, okay? And let's pick the same color, okay? So one is the following. One is how far am I from the Nyquist plot along the real axis, okay? This is something that is called the gain margin. okay? Because now, again, think of this point as -1/k. Now, this is telling me how much larger I can make k while still avoiding the encirclement, okay? Think of this now as -1/k, right? So, going back to your point. And the length of this line is telling me by how big I can make k while still maintaining closed loop stability.
Until where is exactly this red line?
Right, it's to where the point, it's to where the point the Nyquist plot intersects the real axis, okay? So sorry, my scribble here was not exactly precise. Remember that, the Nyquist plot must be symmetric, right, up and down. So the point where these two lines cross must be on the real axis, okay? So it was not on the real axis because I'm a little bit sloppy when drawing these things on the iPad, okay? So this is the gain margin shown on the Nyquist plot, okay? The other important measure that people use is the following. So remember that we talk about this, the unit circle, right? Oops. So think of a circle of diameter of radius 1. And then what we are interested in looking at is how big is this angle, okay? So this is called the phase margin, okay? So this is by how much I would have to rotate the Nyquist plot while still maintaining closed loop stability, okay? Now, the reason why, so on the Nyquist plot, what would make sense is just look at the radius of this circle, right? So how far your Nyquist plot gets from the -1 point. The reason why this gain margin and phase margin are important is because they are actually very easy to see on the body plot, okay? So we have seen the Nyquist condition on the complex plane, right, on the Nyquist plot. What does the Nyquist condition mean in terms of the body plot, okay? So again, if we know that if the open loop system is stable, then in order for the closed loop to be stable, I must not encircle the -1 point. What does it mean on the body plot? Or, what does it mean that you should not encircle the -1 point in terms of magnitude and phase? Essentially what you want is that you want your magnitude of the body plot to be less than 1 whenever the phase of the body plot of the phase of your transfer function is 180 degrees, okay? This is a sufficient condition. It's not necessary, okay? But let's stick to the sufficient conditions, okay? So on the body plot, what this means is that you want the magnitude plot should drop below the 0 dB line. 0 dB corresponds to gain of 1, right? Magnitude of 1. Before the phase plot crosses the -180 degrees line, okay? Remember, this condition is valid only if the open loop is stable. It's only sufficient, it's not necessary. So my recommendation is that, check this condition on the body plot and just trust it, believe it, only if your open loop system is stable and you do not have any no minimum phase zeros, okay? So trust this only if all of your open loop poles and all of your open loop zeros are actually in the left half plane. If you have any open loop pole or open loop zero in the right half plane, don't trust body only, okay? Do a root locus, do Nyquist. Word to the wise, typically when you see in an exam a transfer function which has some no minimum phase zeros or is open loop unstable, that's typically a trick question, okay? So pay attention, okay? So don't trust body only. Let's go back to the nice case. So how do you see this gain margin and phase margin? So what we know is that the gain margin is the distance between the point that has negative 180 degrees phase, right? So which is this is attained at this frequency here. So you see that the phase here is negative 180, okay? So what you do is, at the same frequency on the magnitude plot, you look at, am I below the 0 dB line? Yes, in this case, okay? By how much can I increase the gain and still remain below the 0 dB line? This is given exactly by, this length here, and this is the gain margin. Okay? You understand that on the body plot, if I increase the gain, what happens on the magnitude plot? If I just multiply everything by k, I just shift the magnitude plot up or down, right, if I divide by k. Okay? So that's the gain margin. What is the phase margin? Well, what I look at, okay, so where is the point where my magnitude is 1, where I cross the 0 dB line, which is here. Look at the phase plot, and how far away am I from negative 180 degrees of phase, okay? And this is this distance, this is your phase margin. Okay? And essentially what you will want to do is to try to make this as big as possible, while satisfying other constraints. Okay? Good. So the summary of the previous lecture. So we looked at how to sketch a Polar plot. The Nyquist plot is just the same thing, but just with a symmetric, about the real axis, up and down symmetry, right? Also remember that typically when you draw the Nyquist plot, you want to be careful about, if you have asymptotes that goes to infinity, you have to be careful about how you close them, right? And typically you close them in the clockwise direction, okay? Then we looked at the Nyquist condition, how to check the Nyquist condition on the body plot, right? And how to quickly assess this robustness of a feedback control system by looking at this gain margin and phase margin, okay? At this point, we have looked at 3 methods for assessing the stability of the closed loop based on the knowledge of the open loop transfer function. First one we looked at is the root locus. Root locus is a favorite of mine. I love it. It's always correct if it is applicable. There are some cases in which you cannot sketch the root locus, and those are the cases in which you cannot write the transfer function in the way that we wrote it, in the sense you cannot write it as a rational transfer function, okay? So you can have cases where, for example, if you have a time delay, we will look at it. A time delay is not a rational transfer function, so you cannot use the root locus directly to assess the impact of a time delay, okay? But that said, root locus is always correct if it is applicable. Nyquist, it is always correct, always applicable. It is a pain in the neck. It's kind of, sometimes it can be a little bit hard to draw, it's non-intuitive. Okay, so people usually hate using it, but that's the only 100% reliable method for assessing closed loop stability. Body plot is another favorite. And this is typically what you will use to actually design a control system. Okay? The only caveat is the following, that it may be misleading in determining closed loop stability, and that happens typically when the open loop is either unstable or it has no minimum phase zeros, or both. Okay? So anytime, as I said before, I will not get tired of telling you this, okay? So anytime you have unstable open loop poles or no minimum phase zeros, do root locus, do Nyquist first, okay? And then work on the body plot, okay? Good. So, next point. So now what we have to do is we want to, as I said before, we want to talk about how we set the specifications for the behavior of the closed loop, right? So how do I express my wishes for what I want my closed loop to do, okay? So clearly the number one specification is you want your closed loop to be stable, right? Otherwise, nothing else matters. The thing will blow up in your face, will explode, will melt, will go off-road, will crash, and that's bad, right? So number one thing is you want stability of the closed loop, okay? That said, you may want to have some other performance specifications, okay? So I want my closed loop to be stable, right? But for example, I may want to be stable, but I also want to track commands quickly, right? If I get to my cabin in the woods, in the winter, I want the temperature to become comfortable quickly, right? If I set the cruise control on my car, I want the speed to get to the limit that I set quickly, right? I don't want to wait half an hour for that to happen, right? Also, typically what you say is okay, so I want my system to be stable and meet the specifications, but I also want the system to do that robustly, right? So I don't want my cruise control in my car to go unstable if I put one too many suitcases in the truck, right? I don't want my cruise control to be stable or, yeah, okay, but, just have a light meal for lunch, otherwise the car will go crazy, right? So you want your design to be robust to things like modeling errors, like disturbances, like maybe you have like a headwind in your car, or maybe you're going uphill or you're going downhill, right? So imagine that you have your cruise control and you set it to the speed limit, right, say 120 kilometers an hour, then you're going downhill. So now since you're going downhill, your car is actually going at 140, okay? And then what do you tell to the police guy? Well, sorry, my control system was not working. It's not my fault, right? That doesn't work, right? So you want your cruise control system to keep the speed that you set, regardless of whether you're going uphill, downhill, and things like that, right? So these are all, this is a case of disturbance rejection, okay? So these specifications are typically given using two main paradigms, okay, that we will see in two ways. So one is in terms of time, what are called time domain specifications, okay? So time domain specification means that you're setting, so I want my output, my error to converge to zero within 10 seconds, okay? Okay, or I want my system to overshoot the steady state value by no more than 10% or something like that, okay? Another kind of specification is something that is called like a frequency domain specification, and that's something that says, well, I want you to track all of my commands up to a certain frequency, okay? So I will give you commands that are sufficiently slow, okay? But I want you to track them up to a certain frequency, and then I can say, reject noise, and then know that noise is something that happens at high frequency, okay? So then frequency domain specification really a way to separate, what are the good signals that you want to track, what are the bad signals that you want to ignore, okay? Typically, good stuff happens at low frequencies, bad stuff happens at high frequencies, okay? Okay, and this is what we are going to do next. There is another category, which is this notion of a steady state error, which you can see both in the frequency domain and the time domain, okay? Let's get started, right? So, a simple thing is, so we want to use, say, proportional feedback, right? So what is the setup here, okay? So we have a plant, okay, which has some output, right? We don't like how this plant behaves, so we want to, do some feedback control. So typically what we will do is, something like that. We measure the output. We have some reference input. We compute the difference. This will be my error, right? And then typically what we may want to do is maybe multiply this by some gain k, okay? Okay. And this is a proportional feedback setup, okay? So this is the standard, configuration, okay? So now something that I may want to ask is, what happens if in my, well, clearly, if my reference signal is always 0, okay? What I know is that eventually, since 0 is an equilibrium for my system is stable, I know that my output will also be, eventually 0. Okay, which means that also the error will be 0. Okay. Now, what happens if I, so at a certain point decide, well, you know what? I actually would like my, my reference command is actually 1, or whatever other number. Okay. What happens to the steady state behavior of my system, right? So I know that if the system is stable, the response at the output will not go crazy, right? Will not go crazy, will not go to 0, right? Will it oscillate? No, right? Eventually this will not oscillate, right? Because essentially what I'm giving as an input, as a reference input, is a sinusoid of what frequency? Sinusoid of 0 frequency, right? Okay? So I know that the output, I will have the sinusoid with the same frequency, that is 0, right? So we have a constant. But the amplitude of that sinusoid, that is the magnitude of this constant, is something that depends, right, on what the transfer function is. Okay? So in particular, now what I would like to know is, what is this value that I have at the output? And how does that compare to the value that I have at the reference? Okay? Or in other words, what will be my, my steady state error? Okay? How can I compute that? Any idea? So let's say that, okay, so I give, my reference is eventually 1, right? So the steady state value of my reference is 1. Okay? What I want to compute is the reference value, is the steady state value of my output, y. How can I do that? If this is E, what is this signal here? This would be KE, right? What would be the steady state value of this signal here? P, remember that P is a function, right? So it's a transfer function, it's a function of S, okay? But in this case, how much is S? KE times, so you were on the right track. So we have P, right? And now we are choosing a particular value of S, right? So because we are choosing constant inputs, right? So constant inputs corresponds to a frequency of 0, right? So then this will be K P of 0 times E, right? Okay. So then essentially what we know is that my, what I have here is that, what is it? R, let me write it this way. So E is actually equal to R minus Y, but I know that Y is K P 0 E. Sorry, I forgot. R minus. Okay? Okay? So what does it mean? What I know is that my error at steady state, these are all steady state values, okay? My error at steady state will be given by 1 over 1 plus K P 0. Okay? What does this tell me? Essentially what this tells me is that the larger I make K, or actually the larger K P0 is, the smaller my error will be. Okay? On the other hand, what you will see is that with this structure, okay, if P0 is a finite number, then you will always have some error, okay? And in a sense, this is one of the elements of feedback in a sense, right? So because you need to build up some error in such a way that you can figure out what the right control value is, okay? So essentially the error informs your control action, right? So you see that? Thank you. Yeah, thank you. Okay. Yeah, I got confused because I set the input to be 1. Okay. But yeah, that's right. Okay. So typically what happens is that by making the control gain large, you make the error smaller and smaller and smaller. You will never make it 0 just by this construction, in a sense. Also notice that, okay, so there may be the temptation, so I want the error to be very small, so I make K very large, but what happens? What may happen? Look at this figure here. What if I make my K very large? So then essentially what happens is that I'm shifting this whole curve up, which means that at some point your gain margin will be 0, right? And then you encircle the -1 point, meaning, okay, so you're being too aggressive with your control, you're making K too large, your closed loop system will be unstable. So forget about steady state error. You will not have a steady state because the thing is exploding, okay? So these are some of the issues that will arise. But let's look at this in a more systematic way. Okay, so this is the same thing that I drew before. Now, with the difference that now I'm, instead of considering just a constant proportional gain K, I'm considering the controller is actually can itself be a dynamical system, can itself be modeled by a transfer function. Okay, some transfer function C of S. Okay. Then we have our plant. Typically, we have these things, right? So, for example, we have this disturbance that comes into here. We may have noise that affects my measurements, so on and so forth, right? So, but let's ignore that, this for now. The transfer function from the reference to the error is this transfer function here, right? So it's 1 over 1 plus L of S, where L of S is the loop transfer function, which is the product of my plant and my controller transfer functions, okay? As we did before, if I say that the input is a unit step, that is R of t is equal to 1, that is e to the power 0t, right? Those are all same things. The steady state output will be the value of this transfer function at 0 times e to the power 0t, which is 1, and this is 1 over 1 plus L of 0. Okay, where L is the loop transfer function. Okay, the same calculation that we did, quickly in the previous slide. Okay. So now, as you see, if the limit, so clearly, so if if the limit when s goes to 0 of L of s is finite, and that is something that we call the body gain or the DC gain of the loop transfer function, then the steady state to error to a unit step is 1 over 1 plus the gain, okay? The DC gain or the body gain of the loop transfer function, okay? On the other hand, what you see here, and this is something that you may not appreciate just by using, necessarily using proportional control, is that you actually have a way of making the steady state error exactly 0. How do you do that? Make sure that L of s, the magnitude of L of s, goes to infinity when s goes to 0. How do you do that? You need to have a pole at the origin, okay? So as long as you have a pole at the origin, doesn't matter what your k is, what you know is that the magnitude for low frequencies will go to infinity, meaning that no matter what, your steady state error will be 0, okay? In particular, what we may want to, what we know is that if you have an integrator, so if L of s contains an integrator, that is, if L of s has a pole at 0, then I know that my steady state error to a unit step or to a step will be 0, okay? That's great. More in general, not that often really, typically only when people ask you questions in exams. What you may want to have is, you may ask that the closed system has a 0 steady state error to a unit ramp, okay? Not only to a unit step, but say, so if I tell you to just keep increasing the temperature or the speed on a ramp, then I want you to follow that command precisely with zero error in steady state, okay? This is one of the things that you always find in controls textbooks. Kind of like it bothers me because, when do you do that? Never, right? Because, typically you never have reference inputs that are diverging, right, in steady state. But this is what you find in textbooks, okay? So this is what you need to know, right? Okay, so anyway, let's say that sometimes you will be asked to say, okay, I want to have a 0 steady state error to a unit ramp of some order, okay? So unit ramp of 0 order is the unit step. The unit ramp of order 1 is just a straight line. The unit ramp of order 2 is a parabola, right? Okay? Now, if you think of these things, so okay, let's draw it here. So this is the order 0, right? R and T. This will be order 1, and this is R of T is equal, say, 1, okay? This is R of T is equal to T. The order 2 will be something like that, right? Is a parabola where R of T is 1/2 T squared, okay? How are these related to one another? You see that this one is the integral of this one, right? This one is the integral of this one, right? Okay, so how do you get ramps of nth order? Just integrate the unit step n times. That's what the unit ramp of order n is, okay? How do you compute the steady state error? Well, essentially the way that I wrote this formula is the following. So just imagine, okay, that I have my system, okay? What I want here is a ramp of order, say, 2, okay? So I will just say, okay, so let's just put a step here and just integrate it twice. Okay, remember that 1 over s is the integrator, right? Okay. So then what is the transfer function, from here to here? Well, you just have a series of 1 over s squared, right, or 1 over s to the power m, if you want to look at the mth order ramp, okay? And then you have your closed loop transfer function, okay? Okay, which is this, well, actually this is the sensitivity function, is the transfer function from this input, from this input to the error, okay? Okay, so then essentially my steady state error will be computed by computing this limit, okay? Notice that e to the power st, when I take the limit, this will just become 1, so you can just disregard it, right? So essentially what you see is that in order for the steady state error to be 0, for example, for some value of m, then you need to have at least one more integrator, right, than the order of the ramp. Okay. So, and you actually summarize it here. So essentially, if you want to have a finite error to a unit ramp, so then this is the so essentially the result, the value of this limit really depends on the number of integrators that you have here. Okay. Okay. So in particular, we will call. Don't ask me the reason. It's again one of those jargon things that evolved during the past 5 decades. Okay. So when people talk about the type of the system, it actually means how many integrators does the system have, okay? Then the steady state error to different orders of ramp depends on this type of the system, that is, depends on the number of integrators that it has, okay? So if the type is 0 and the input is a unit step, that is 0th order ramp, then we already know that the steady state error will be 1 over 1 plus the body gain, okay? If I have 1 integrator, then my steady state error to unit step will be 0. If I have more than 1 integrators, also my steady state error will be 0, okay? Now, however, what if I give a unit ramp as an input? A type 0 system, a system that does not have integrators, will actually diverge. The error will diverge, okay? You can understand it, right? So if I give a constant input, I will always miss it by something. Now, if I give an input that is constantly increasing, then my system will not be able to keep up, right? So then the error will diverge, okay? So if I want to have a finite steady state error to a unit ramp, I need to have at least 1 integrator. If I want to have 0 steady state error to a unit ramp, then I need to have at least 2 integrators, okay? So on and so forth, okay? So you can see how this little table is built, okay? So again, anytime somebody comes to you and asks you, design a control system such that the steady state error to a unit ramp is 0, then what it means is, in plain English, is just make sure that there are 2 integrators, okay? Yeah.
Is the gain, the magnitude, is that right?
So, yeah, so the body gain is is essentially, so you remember very early on, clearly I couldn't explain you why, okay? But what I said is that, when you have a transfer function or, some transfer function g of s, right? You can always write it as in the form, what I call like a k body. And then what you need for that k to be the body gain is you want to write all of the factors as, say, s over z Z1 plus 1, okay, over S over P1 plus 1, okay? So whenever, why am I doing this? Because if I do that, just give me a second, let's conclude this thought. If I do this, then when I take the limit, when S goes to 0, all of these things will be, all these factors will actually be 1s, right? By the way, you can also have integrators, something looks like that, okay? So in this case, you cannot really take the value at 0, you only take the limit, but you see that in the limit, all of these factors will essentially go away, right? So what you're left is K body and the integrators, okay? So that's what we call the K body, and this is what gives you this steady state error, okay? Let's take a break, we'll continue afterwards. Okay, let's resume. Okay, so essentially what we were saying before is that whenever somebody asks you, I want you to have finite state error to an M order ramp, then essentially they're meaning you need to have M integrators, okay? If they tell you I want to have 0 steady state error to an M order ramp, then what they mean is that you need to have M plus 1 integrators, period, okay? Again, this is language that you typically see in exams, okay? Or if you have a particularly, unfriendly boss, right? But, in general, what you will have is just put these many integrators, okay? So essentially, this is what you need, right? So in particular, you know that, for example, if you're doing cruise control, then you know that you want to have 0 steady state error, then you know that, you will have to put an integrator in that system somehow, okay? Now, okay, so how do we express these specifications in the time domain? What you typically do is you refer to a second order system, okay, and then write your specifications based on this, assuming that the behavior is the same as that of a second order system. Then, what are some characteristics that you want? Okay. And, there are things like, okay, so for example, you might want to say, a second order system, typically you kind of like overshoot and oscillate and then eventually settle. Oh, thank you. That is a problem. Okay. Yeah, sorry about that. Okay, so typically what you have is second order system is something that oscillates and eventually reaches a steady state value, right? So things that may be important to you is how quickly the response gets close to the steady state value, right? And so something is called the rise time. By how much the response exceeds the steady state value, that is called the overshoot, is typically expressed as a percentage, okay? And then how quickly your response eventually settles to within some margin from the steady state, okay? So then what you do is, just as I said, just write it as the step response of a second order system. We know that the step response of a second order system is written as this, right? Is essentially 1 minus, where 1 is the steady state value. Let me write here. Okay, times 1 minus E minus sigma t, sigma is the real part of the poles, right, times the cosine of omega t, where the omega is the real part, is the imaginary part of the poles, okay? Good. This is one way of writing it. This is the canonical form of a second order system that you see that is expressed in terms of natural frequency and this damping ratio. The natural frequency, you get it by just summing the, that's the magnitude of the poles, right? So just sum the real part square plus the imaginary part square, take the square root, that's your natural frequency. Your damping ratio is given by the ratio of the real part over the imaginary part, okay? And, the usual drawing, right? So on the complex plane, real part, imaginary part. Remember what the response looked like of a second order system, right? So essentially, when you're far, on the real axis, then you have the exponential that is decaying. If you are on the imaginary axis, then you have just a sinusoid, right? If you pick any direction, right, then what you will have is that the shape of the response will be something that, okay, so it will be something like that, right? But the shape of the response, if you move along one of these directions, the shape does not change. The only thing that changes is the scale on the time, okay? And right here, it looks like something that is undamped and is oscillating. Here is something that is not oscillating and is just decaying. And any other direction, here what you will have is, for example, here what you will have is, so you have a decay, right? But then the oscillation is much, much slower than the decay in a sense, right?
Question.
Yeah.
What do you mean with direction? Are you keeping the radius the same? I'm talking about the part where you said that it keeps the same shape.
Okay, so essentially the direction is really giving you, okay, so these are all directions with a constant damping ratio. Okay, you see? So essentially the damping, so let's say this could be, damping ratio is 0.1, this is damping ratio is 0.5, something like that, okay? Okay, and the point here is that the damping ratio determines what is the shape of the response. The natural frequency, that is how far you are on these lines, determines what is the time scale of the response. Okay? So, the rise time depends primarily on the natural frequency. This is what you see on textbooks. For me, it really depends on the frequency, okay? Because, for example, what is the rise time to this point? What is the phase in your sinusoid at this point? Was 0? Pi? Here it's pi over 2, right? So how quickly do you reach it? It's just pi over 2 divided by omega, okay? So this is the rise time to 100%. There are other formulas that you find in your textbook. You pick a different textbook, you find different formulas for these things. These are all kind of like rules of thumb. On Goodseller's book, he reports this formula here. The time rise, the 90% rise time is 0.14 plus blah, blah, times this expression here, whatever, okay? Doesn't really matter. The point is that what you should remember is that the rise time really depends on the frequency of the response, and then of the pole, of these closed loop poles, and then you want to put the frequency where you want it. The peak time, again, depends on the frequency. This is the time at which you reach the peak. The phase at the peak is pi, so how do you find this time? Is pi over omega, okay? Again, depends on the frequency. Percent overshoot depends on the shape of the response. If it only depends on the shape, it depends on the damping, okay? You can do the calculations. It doesn't really matter. So what you should do the calculation is really this formula here is minus sigma over omega times pi. You can think of it as, do calculations, what you get is this thing, okay? What you have to remember is that the bigger the damping ratio, the smaller the overshoot, right? And in particular, when the damping ratio gets to 1 or more, you have an overdamped system, you have 0 overshoot, okay? Settling time depends only on the real part of the poles, okay? And the real part, that the amplitude of the response will vanish as e to the power minus sigma t. By what time e minus sigma t will be less than, say, 2%? Well, that has to do with some logarithm somewhere. You have to invert the exponential, right? And this is how you compute the settling time, okay? So settling time is given by this logarithm over sigma, and you can also compute the sigma that you need based on the settling time. Okay? Clearly, if you have a first-order system, then it will have no peak, will have no, I mean, the only relevant measure is the settling time, sigma. Okay? Now, everything okay? Okay, so essentially things to remember are, if I tell you that I want a percent overshoot of, say, 20%, a peak overshoot of 20%, really what I'm telling you is that I want a damping ratio of 0.7. Again, it's one of the things that people tell you in the exams, or bosses who are kind of particularly unfriendly to you, right? But there is no point in saying, I want a 20% overshoot. 20% overshoot just means damping ratio, 0.7, period, okay? Settling time, essentially that determines what is the real part of your closed loop poles, okay? Rise time is really not that useful, but really determines the frequency of your closed loop poles, okay? Now, the question here is, what if the closed loop system is actually not second order, but is more than second order, like higher order system? The reality of it is that most systems behave qualitatively like second order system, okay? So then what we will do is, for the purpose of setting the specifications, we will approximate any higher order system as a second order system, okay? And the way we do it is based on this idea of dominant poles. Essentially, we will ignore all the poles except two, okay? How do I choose these two? These are the ones that are essentially the closest to the origin. What does it mean to be closer to the origin? These are the poles that have a real part that is smaller in magnitude, meaning that they will take a longer time to decay to zero, okay? So these are the poles that essentially dominate the response, because all the other poles, the components of the response due to the other poles have vanished quickly, like a more, has vanished earlier, right? So in a faster way, okay? The only thing that you have to be careful about is that sometimes you have some poles that are close to the origin, or closer to the origin than others, but they're near some zeros, okay? Then the effect of those zeros, remember, is to set the residue of that poles to be close to zero, meaning that even though these poles linger for a long time, their net effect is very small anyways, right? So as a general rule, choose as the dominant poles the ones that are closest to the origin, assuming they're not too close to zeros, okay? If they are close to zeros, just disregard them, yeah?
If we had an integrator, would that mean that would be one of the dominant poles?
So remember, so here what I'm talking about is the closed loop response. So typically what you have when you have an integrator, and then you put in a closed loop, the pole at the origin will move somewhere else, right? So you remember the root locus, okay? So even though you may have an integrator in your loop transfer function, the closed loop does not necessarily contain an integrator, or typically will not contain an integrator, okay? So it will move, right? And then what we are looking at for the closed loop, for the specification, is the closed loop poles, and in particular, the dominant closed loop poles, okay? For example, if we have a third order system, something like that, right? So this has a pole at -5, will decay as e to the power -5t, and then you have two poles at -1 plus or minus 5j, right? Will decay as e to the power -t. And this is the response, right? So what you see is that, okay, the full response is the blue. The red response is actually the response computed considering only the dominant poles. You see that the two are not too different. They are different, right? But not too different, okay? Why is that? because the stuff that I'm neglecting, s plus 5, is actually something that is, the error that I'm making is essentially declining, vanishing as e to the power minus 5t. Okay? This is another example. So now we have a pole at negative 0.5, right? And then we have these other poles at negative 1 plus or minus 5j, like before. But now you see that the effect of this pole is actually dominant. Okay? And in fact, you see on the response, again, that the response of the red response, which is the approximate response, tracks the full response, kind of accurately, because the difference is this oscillation that decays quickly. Yeah.
There might be a mistake in one of the slides.
Okay.
Go back 2 slides.
Yeah.
There is written the dominant poles are the ones with the largest reading part. Shouldn't they say with the smallest reading part?
Yeah, I think that I think, so remember that the real part is negative, right, on the left, right? So essentially what I meant is the poles that are the closest to the origin, they're the most to the right, okay? So it's either the smallest magnitude if they're negative, or the largest if they're positive, right? If I say just the largest, that captures both cases, right? So it's the poles that are actually the furthest to the right. Okay? Okay, but thank you, good point. Okay? This is another case where, again, it was like before, right? So we have the pole at negative 0.5, but you see that we have a 0 at negative 0.6. So actually the effect of that 0 is to make the response of that particular pole negligible, and then you see that the approximation with just these 2 poles is actually the good one in this case. Okay? There is no hard and fast rule. You may have cases in which there are no dominant poles and you really have to deal with the whole system, but those are kind of like typically rare. What was the question?
The previous slide.
Yeah.
Is there a reason why we can approximate that only for one of the poles and not use 2 of them? Is it just because the other one has the same behavior?
So essentially what we said is that we approximate this with these 2, right? The complex conjugate, right? Because, no, actually, so we approximate it with this one, right? Because this one is the pole that is the furthest to the right, right? So what was the question?
No, because as I said earlier, we use the 2.
Right. So in this case, what you see is that the dominant poles is actually 1, and it's fine. Okay. Just remember that the specification on a single pole are actually simpler, right? So you have no overshoot, right? Rise time and settling time are actually the same thing, right? Okay. Other questions? Yeah.
How do we get 113 to 0.5 in the denominator?
Super excellent point. Thank you very much. Okay, so the one thing that you had to do is you just cannot just get rid of one of the factors, okay? So what you had to make sure is that the DC, the body gain is the same, okay? So just, remove whatever needs to be removed and just make sure that the body gain is the same, okay? In this case is, what is it? What is it in this case? Yeah, not sure what I did here. We'll get back to you on this. But essentially the point is that if you want this to approximate this, at least they should have the same behavior as steady state, right? So just make sure that the body gain matches and then delete the factors that you don't need. Okay? Other questions? Yeah. We did that, several lectures ago, right? You can either do it algebraically. What we did is compute this, we use this cover-up method, right? Essentially what you do is to compute the residue at one pole, you compute, you look at all the distances from all the zeros, the product, divided all the distances from the other poles, okay? That's how we compute the residue. We did that several weeks ago, so maybe go back and review that material, okay? Okay, so these are the time domain specifications, impose constraints on the location of dominant closed-loop poles, okay? Settling time means that you want the real part of the closed-loop poles to be to the left of some line. The peak overshoot is really a constraint on the, on the damping ratio, and you want the damping ratio to be more than some value. Rise time constraint, essentially what you're saying is that you want that the the frequency is, the imaginary part is large enough, or also the natural frequency, the distance from the origin is large enough, okay? So this is easy to do on the root locus. If you look at the complex plane, essentially what you want is to pick locations of the closed loop poles. You want to pick locations on the root locus branches that are essentially, to the left, or I don't know how to. So you want to be to the left of this line, right? So that the settling time is small enough. Otherwise, your system is too slow, right, in settling down. You want your damping ratio to be smaller than something. Otherwise, your peak overshoot is too large, okay? And typically what you want is also the distance from the origin to be large enough, okay? So that you get like a good rise time, okay? So then typically what you want is just make sure that your closed loop poles are somewhere within this area, okay? So this is the good region, okay? Yeah.
So you want your dominant poles to be there?
Yeah, you want your dominant poles, your dominant closed loop poles, right? So of all the branches of the root locus, pick the two that remain closer to the origin in a sense, right? And make sure that those ones are within this region, okay? Now, the exact values depend on, you can say that, this is, this is, negative 0.2, whatever, right? If you want your system to be faster, this can be -2, right? Typically what you say for the damping, like a good value for damping is typically 0.7, okay? But, all these things depend on the particular, on the specifics of your design, okay? But in general, this is what the time domain specification leads you to, right? So just make sure that the closed loop poles are somewhere within this red region, okay? Okay, now let's look at frequency domain specification. Why are we interested in the frequency domain specifications, okay? So if you remember the sensitivity function, this is the sensitivity function is this one, is the transfer function from the reference input to the error, okay? Or from the output disturbance to the error is the same transfer function if you do the calculations, okay? So if you want small errors when I change my reference input, what I want to have is I want S to be small, right? Because that's the magnitude of my error, okay? So I want S to be small in such a way that I have good tracking, small errors, good disturbance rejection. On the other hand, if you look at the transfer function from the noise that appears here to the output, is this other function, the complementary sensitivity function, which is this one, right? So if we do not want to see the effect of the noise on my output, then what I want is I want this transfer function to be small. And this is where you have problems, right? Because, well, I want S to be small, I want T to be small, but what I know is that S plus T is equal to 1. So can I make both of them 0.1? No, right? So how get out of this problem? And this is exactly why the frequency domain specifications are so important. So typically what happens is the following. When you steer your car, right, or you set the temperature, you do it at low frequencies. When you drive your car, you do this? No, right? So you typically, you'll give like a smooth, slow commands, right? When you set your temperature, you say, I want 24 degrees. No, I want 19. No, I want 30, right? So no, you set 24 and that's it. And then you forget about it, right? So that's a zero frequency, okay? So typically, anything that is human, and actually your brain works at about, how fast your brain is? Your brain typically works at around, order of 10 hertz or, roughly, maybe 50 hertz or something, okay? In terms of, and for example, your reaction time is probably of the order of a tenth of a second or something like that, okay? So there is no way that a pilot will drive something at a frequency that is much higher than 10, 20 hertz, okay? So there is absolutely no need to track commands at more than 20 hertz, period. That's just the way it is, okay? Also, typically disturbances that come out of physical processes, for example, wind or uphill, downhill profile, those are also happening at relatively low frequencies. On the other hand, the noise that you get in your sensors, is the electronics, right? The noise that you have is typically at high frequency. And that's exactly how we resolve that conundrum, right? So because now what we want to do is, okay, we will make S small at low frequencies. It's fine for us to have T large at small frequencies because at low frequency I have no noise. On the other hand, I will want to make, so essentially this is saying, just make sure that the commands are tracked with, say, max 10% error up to a frequency of 10 hertz. It's a very reasonable specification, right? But then you say, okay, so, but then, anything that comes into the system at the frequency of, say, 100 hertz or more, that's not the pilot, it's not the driver. That's noise. Anything comes at a high frequency is noise, so it's fine with me to reject it, right? So it's fine with me to have, what I will want to make is make T small at those frequencies. And it's fine with me to have S to be large at those frequencies because I know that these are not a pilot command anyway, okay? And this is exactly how you resolve this thing. Now, the problem is that, I'm setting these specifications on this closed loop transfer function, the sensitivity and on the complementary sensitivity. What we say is that everything we do in this course is about leveraging as much as we can the open loop transfer function to figure out how the closed loop will behave. And this is exactly the point. So can we write this specification in terms of the open loop frequency response? Indeed, yes. So for good command tracking, disturbance rejection, we want that S of j omega, which is 1 plus L of j omega inverse, if you take the magnitude, we want this to be small at low frequencies, okay? So we want L, so if you want this thing to be small at low frequencies, how do we make this small? By making L large, right? So essentially what we want is L of j omega to be large at low frequencies, okay? So then typically what you do is you say, that the magnitude of S of j omega must be less than, say, 1 over omega 1 of j omega for some function 1 omega 1 that is larger low frequencies. And essentially what this translates to is, 1 plus L of j omega greater than this W1. If L of j omega is large, then 1 plus L of j omega can be approximated with L of j omega, right? If I want the absolute value, the magnitude of 1 plus L to be 1 million, then what does it matter? I can just say that the magnitude of L must be 1 million, right? Because one part out of a million doesn't matter, really. Okay? So then we will write that L of j omega must be greater than some W1 of j omega. Okay? So we'll show pictures. Okay, let's go here. So essentially what I'm saying is that at low frequencies, I will put this, think of it as a low frequency obstacle, okay? What I'm saying is that I want my body plot, the magnitude plot, to be larger than some curve that I specify, okay? In particular, this in general would be something like, okay, so this must be more than 40 dBs to up to frequencies of 0.1 radian per second, okay? So essentially what it means is that the body plot must be above some obstacle at low frequency, okay? For noise rejection, what we want to do is do something like that. We want these to be small at high frequencies. Notice that if T of j omega has to be small, then also L of j omega has to be small, right? If L of j omega is small, then 1 plus L of j omega is approximately 1, okay? So then I can approximate this complementary sensitivity just by the open loop transfer function, okay? So then what I would want to say is that T of j omega must be less than 1 over some omega 2 for some function omega 2 that is larger at high frequencies, meaning that now I want L of j omega to be less than 1 over omega 2, okay, at high frequencies. And again, this is this obstacle, high frequency obstacle, something like this, and what I want is my body plot to be under this obstacle, okay? Remember, I want high gain at low frequencies so that I get small steady state error or small error at low frequencies. I want low gain, very small gain at high frequencies so that I reject noise, okay? What happens in the middle? The bandwidth of the closed loop system is defined as the maximum frequency at which you are essentially following the command, okay? Roughly, okay? So then the complementary sensitivity is more than 1 over square root of 2. Essentially, the output can track the commands to within a factor of approximately 0.7, okay? You may have noticed that, like physical systems do not like to move too quickly, right? So if you shake something slow enough, then that something will follow your commands, right? But if I take my car and start doing that, the car will keep going straight, right? So essentially my shocks, my tires will absorb all that vibration and the car will not respond that quickly, right? How do you measure this maximum frequency at which the system will actually follow your commands? This is exactly what we call the bandwidth, okay? And essentially this is the maximum frequency at which your system will follow your command to within 0.7, okay? 1 over square root of 2. And as it happens, assuming that the phase margin is about 90 degrees, this is where things are exact, but essentially what you get is that your closed loop bandwidth is actually given by the crossover frequency in your body plot. That is the frequency at which you cross the 0 dB line, okay? And so essentially we are done. So typically what you do in designing a control system on the body plot is the following. Make sure that on the left, you are above some obstacle that is giving you my, tracking performance. On the right, I'm below some other obstacle that tells me how much I should reject noise. And then I had to cross the 0 dB line somewhere, at essentially something that corresponds to the bandwidth that I want for my closed loop system, okay? And then the last thing is that typically what you want to do is when you cross this line, you want to do it to be kind of shallow, okay? You don't want to cross it too quickly. Why is that? Let's see. If somebody catches it.
sharp decrease or increase just if we increase our frequency a little bit or decrease it a little bit?
That is not necessarily bad, right? But you remember, at some point we said that, the slope of the magnitude plot is actually related to the phase, right? And in particular, if the slope is very steep, what happens to the phase? The phase is very negative. Okay, I see. So if the phase is too negative, then you are below minus 180, and then you are getting close to instability, okay? So typically what you want to do is stay above this line, stay below this line, cross at a certain point, but cross it as shallow as you can, okay? Because if the slope is shallow, then your phase is not very negative, meaning that your phase margin is large, okay? Typically, you will want to cross this at say at the -1 slope, at a minus 20 dB per decade slope, okay? That will give you 90 degrees of phase margin, which is plenty, typically, okay? We could stop the course here, okay? So this is all you need to know, okay? And in the next few lectures, we look at what are some ways that you can actually achieve that, okay? Oh, actually, I'm early today. Well, didn't happen very often, okay? But essentially, this is all you need to know in terms of specification. Okay, so summarizing. If somebody writes to you, I want to have a steady state error of such and such, possibly 0 to say unit steps. Translate that to English, okay? So essentially, steady state error means that your body gain must be larger than something. If they want to have 0 steady state error to unit steps or unit ramps or something like that, that tells you, okay, so your body gain must be such and such, and you need to have at least this many integrators, okay? So this is something that must become like hardwired in your brain. Right? So when somebody tells you something about the steady state error, what that means is body gain large enough and or number of integrators large enough, period, okay? That's automatic. There is no other way that you can get 0 steady state error to a certain order or ramp without having that many integrators, okay? Those integrators can be in your plant. If they're not in your plant, you have to put them in your controller, okay? So then your COS will contain these many integrators, period, okay? Not even 5 seconds, this is immediate, okay? Okay? Time domain specifications. So these describe how you want your response to look like when you approximate it as the response of a second order system. Okay? So these are easy to formulate, to understand. These are easy to check. If on MATLAB you use the CISO tool and then you see the step response, you can get an idea of what it means. The problem is that there is no easy way of translating them directly into design principles, okay? Really, the best way that you can meet the specification is just looking at the root locus, make sure that the branches to the root locus are in that good region of the complex plane that you like, and then trial and error. Move those things on the root locus a little bit, look at the step response on MATLAB, okay? But the time domain specification are typically more for the so more like a naive, okay? The pros really think in terms of frequency domain specification, okay? Frequency domain specification means that, okay, so I want to have like a small error, not only a frequency 0, not only a steady state, but maybe up to a certain frequency range. What that means is that the magnitude of the body plot must be larger than something up to a certain frequency, period, okay? then I may want to say, okay, I want to reject noise above, say, 100 hertz by at least a factor of 1,000. Fine. Make sure that your magnitude body plot gets to below negative 60 dB when you get to 100 hertz. Okay? I want to have a bandwidth of 20 hertz. Make sure that, or 100 hertz or whatever, say 20 hertz. Make sure that your crossover happens around 20 hertz. Okay? People may ask you, I want to have a phase margin of such and such. Make sure that your phase is far away, sufficiently far away from negative 180 at crossover. Okay? And then this is really all there is to it. Okay? And the rest is just getting some practice with how to steer this body plot. Okay? Okay, let's stop here. I'll see you guys next week.